So we'll go to our next speaker here, Dr. Melissa Wett. She's a research scientist at Lockheed Martin Space Advanced Technology Center, and will be presenting Perforene, a robust, highly efficient membrane solution for lunar water purification.
Thanks for the introduction. You can go to the next slide. So as we know, in situ research utilization is a critical enabler of sustained human presence on the moon, Mars, and beyond. Within ISRU, a primary focus of is water, which a lot of us have been talking about today. So water is critical not only to sustaining human life, but can also be used to generate fuel and energy. Several current and future NASA programs, including the Lunar Reconnaissance Orbiter, Viper, Lunar Flashlight, all are focused on identifying water deposits on the moon. Now, terrestrial reverse osmosis, or RO technologies, are poorly suited to extraterrestrial applications. Particularly, current systems are extremely inefficient when operated at small scales and volumes, which would be we would be expecting to use in an ISRU type situation. And furthermore, the membranes we use for those separations are unlikely to withstand the harsh space environment. Therefore, alternative ISRU-oriented RO technologies are desperately needed. Next slide, please. So I'd like to introduce our solution to that, which is Perforene. So Perforene is a combination of the words perforations and graphene. So graphene being a 2D carbon allotrope with unique chemical, thermal, and mechanical and optical properties that we take and then perforate precisely with sub-nanometer pores to permit the passage of some ions and molecules while blocking others via size exclusion. With the technology we've developed, we are able to grow and transfer large area defect-free sheets of single-layer graphene onto arbitrary substrates, and then induce precisely controlled pores in the 0.4 to 20 nanometer size range. So in this image on the bottom left, you can actually see one of our membranes. The scale bar is an inch, so it's actually a fairly large piece of graphene. And then on the right shows an example of varying levels of perforation under an electron microscope. Next slide, please. Okay, so why is Perforene such an attractive candidate for RO? So there's two key parameters that we look at in RO. So one is permeability, or how easily can water actually pass through the membrane. And the second is rejection efficiency, or selectivity, which is what fraction of the target species are blocked. Now, Perforene-based membranes are about 1/130th of the thickness of a conventional membrane, and which, through simulations, we know that through physics, we know that a thinner membrane directly corresponds to having a higher permeability. So we expect that Perforene would have a significantly higher permeability while maintaining the rejection efficiency of conventional membranes. Additionally, Perforene-based membranes are well suited for the space environment. They're thermally robust, limited only by the operational range of the support membrane. Perforene itself is extremely chemically and environmentally resistant to a variety of treatments. And due to its unique chemical properties and its atomic smoothness, we expect Perforene to have a lower incidence of clogging and fouling, leading to it to be usable over a longer period of time. Next slide, please. So, like I said, thinner membranes correspond to higher permeability, so which directly translates into a lower amount of energy requirement for, or pressure applied for operating the system. So we've done molecular dynamic simulations, which are shown here, to predict what the permeability of Perforene is. And so on this plot, the y-axis is rejection efficiency and the x-axis permeability. And what you can see is that Perforene is expected to be more than 100 times permeable than a commercial membrane that is used in reverse osmosis. Next slide, please. So so far we have some fairly promising preliminary experimental data. So in this slide, I'm showing some of our reverse osmosis data for one of our membranes, which you can see here in the image. So we built a prototype cell using with an RO membrane comprised of perforene on a polyimide support, and which we evaluated against our representative salt solution and saw that we could achieve rejection efficiencies near 70% with low water volumes and pressures. Now we expect that layering multiple perforene sheets on top of one another is expected to greatly improve rejection efficiencies with only a small impact on permeability itself. Next slide, please. So looking forward, we have a lot of work planned with Perforene. So in Q4 of this year, we'll be working with Lockheed Martin's commercial and civil space teams, which are developing values for system volume, contaminant concentration, and pressures of interest to inform representative RO testing for an ISRU environment. We're additionally, we'll be looking at other contaminant spaces of interest to evaluate RO membranes for solutes beyond just salt. Besides that, we'll be doing environmental testing to look at the resiliency of perforene membranes. So looking at temperature, vacuum, corrosion, and evaluating the RO performance before and after exposure to representative temperatures that a membrane might see in a lunar environment, as well as desiccation and vacuum, whatnot. Next slide, please. All right, so in summary, perforene shows promise for ISRU. We know that ISRU is for, pardon me, ISRU for water generation is a critical enabler for sustained human habitation in extraterrestrial environments. We've shown that perforene can be a promising membrane technology for reverse osmosis in extraterrestrial applications. And our preliminary experimental data and theoretical data suggest that this membrane is extremely well suited for developing low power, lightweight systems in these environments. I want to thank you all. Feel free to reach out to myself or my colleague, Michael Wisser. Our emails are in this slide, and I think I was able to get us back on time. So thank you.
Yes, you were. We got 3 minutes if anyone has any questions. No one's posted one in the chat, but if anyone does, feel free to ask. If not, we'll move on. Here we go. What membrane configurations has this been tested with? Flat sheet, hollow fibers, etc.
So far we've done a flat sheet type system where we're making essentially a sandwich cell with a single flat membrane.
Okay. Well, if there's no other questions, I think we'll just go ahead and move on to our next speaker.